Welcome, this is the first video in the Python's data structures playlist, and this video happens to be on lists in Python. So essentially this video is categorized into three parts. First part where I actually introduce you about the list data structure, and then we move on to seeing some really common methods that are frequently used when you code in Python using lists. And then third part actually includes some more details regarding lists. For example, we are going to see some time complexity related proofs, and also we are going to see how Python's list can store multiple types of data at the same time. So don't wait, let's get started. Before we move on to seeing code on Python lists, I would like to explain you briefly what Python lists actually are. Lists or arrays are basically sequence of items stored contiguously in a memory location, So let's say that I have this list and it stores every cell in this list will store an item. Let's say I'm having a list of integers. So I can store 100, 20, 1, 3, 5, 85, 400, 30, 600, something like this, or so on and so forth, depending on how many items we want to store. So this is a list. And another thing is that every cell is associated with an index. So first cell will have an index of 0. Second cell will have an index of 1. Third cell will have an index 2. Then 3, 4, 5, so on and so forth. Now, let's say the name of this particular list is A, then A of, this is how we perform an indexing operation on a list. So I'm doing indexing. So if I do A of, let's say 4, then this means that I'm actually trying to access the item present on index 4. What is that item? So index 4 is this here. So it contains an integer 5. Right? So let's say I want to, I do this. This means that I'm actually trying to access an item that is present on index 0, which is actually the first item of the list. So I hope that you have a basic understanding. Another thing is that in the memory, let me just clear up some space here. In the memory, every cell will be placed contiguously, which means their memory location will be one after the other. So let me say that the first cell is having a memory. Let's say every cell is of 4 bytes. So the first cell, if first cell address of the first cell is 0x00, then plus 4, then the next cell will be of 0x04, then next cell will be 0x08, and so on and so forth. So I hope that you understood that the list actually stores all the items contiguously in the memory, one after the other. And we can also perform indexing on this. And actually we can do a lot more operations on a list in Python based on what Python has to offer. That is what we are going to see in the next section. Just after this particular briefing on list, we are going to see the code and we'll understand much more about Python lists and most commonly used methods on Python list. So anyways, so let's move on and see why Python lists are also called as mutable dynamic arrays. So this is something really interesting. So Python lists are also called as mutable dynamic arrays. So I hope that arrays we have already seen. Arrays or lists, we have just understood what lists or arrays are. But let's focus on mutable and dynamic. So mutable means here is that once you have initialized or stored some item or some values in your list, let's say that you have stored integers again, let's say it's 500, then 1000, then 800, something like this. Now, this list is also called as A. And going further, going down the line, you want to change this 1000 and you want to store 600 in place of this 1000 in the same list object, in the same list. You can do so. So you can change that 1000 to, let's say, 600 and then 800. You can do it in the same list. This is the same list. Why this change is allowed? The reason for this is that you can actually modify the content of the list Reason for that is because lists are actually mutable, and that's what mutability means. You can change the content or the items or values that are stored inside a list. So I don't want to go much in detail and digress from here and explain you what mutability or immutability is. I already have a separate video recorded on mutables versus immutables in my Python tricks playlist. If you want, you can go ahead and check that out. I'll put the link to that video in the description. So anyways, moving further, let's see why lists are also called as dynamic. So this is pretty much interesting. So Python lists are also called as dynamic. Why is so? If you are coming from C background, or if you have ever coded in C, even if you haven't coded, then let me tell you that in C, whenever you create an array, you actually need, let's say you want to create an array that can store integers. So you have to declare something like this roughly, and then max size. What this means, you're telling C that you want to create an array, and the total number of cell that array should hold in the memory is equivalent to this max size. Let's say I make this max size as 10. Then what am I telling eventually is that create an array that should hold up to 10 cells in the memory. I'm not sure how many cells I have created here, but indexing starts from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah, exactly 10 items. So this is what I mean when I am actually trying to create memory location for the list in C. However, on the other hand, in Python, you don't need to provide any such value or any such size. So in C, what happens? You can store up to 10 items. That's all. You cannot do anything much. If you want to store more, then you will have to create another list. However, in Python, let's say that you have created a list which is empty initially. But let's say that after you have created, you want to fill in items in this empty list. Python will allow you to do that. You can, so there is one method, append. We are going to see that in code, but for now, just bear with me. So you can do something like this, a.append. Let's say you want to insert 90. Then Python is going to insert 90 in the same list. How this happens? Let's try to just quickly understand that. Let's say that you have a list that contains 5 and 4. Now you want to insert another item, which is 7. Let's assume that. But there is no space to insert 7. Then Python is actually going to create another list, a bigger list, which will have size as big as 2x of the previous list. So 2x, this list had 2 cells. So the size was 2. So double this size, double of this size, which will be 4. So 2x will be 2 into 2. It will create a new list which can hold up to 4 items, and it will copy the older items to the newer list, 5 and 4. And because you are trying to insert 7, it is going to insert 7 in the next location. So this will all happen under the hood dynamically. You don't have to know or worry about it. This will be taken care by Python itself. And this list will still have one place, one empty spot to fill in. So you can again store some item here. So after that, let's say you stored 9. Now after that you want to store, let's say 15, but now again there is no space. Then probably Python is going to create another bigger list which can hold up to 2x item of the previous list. So the previous list held 4 items. Now the new list can hold up to 8 items. So 1, 2, 3, 4, 5, 6, 7, 8. And it will copy all the items from the older list to the new list and till here. So 5, 4, 7, 9, and then it will store 15 here. And that's why the Python lists are called as dynamic. So you don't have to worry about how Python resizes or increases the size dynamically as in when you fill in the items in your list. So I hope that you have a rough understanding of Python lists. So let's move on to seeing some code and we will understand about Python lists a lot better. So on the screen, you will be seeing 2 panels. One is on the left side, which I'm highlighting right now. So this is the panel on the left where I'll be writing the code. One on the right side where I'll be running the same code and getting the output for you. But right now I haven't everything is commented, so you will not see any output. And now as part of the lists, what are we going to cover? So we are going to start with the basics. So we'll see that how to create a list, how to initialize a list, then how to index and perform an indexing in a list, like given an index, figuring out which item is located at that particular index, and then what is the length of that list. We are going to see that. These are basics, and then we're going to move to the commonly used methods on lists. If you have ever coded in Python and worked with lists in the past, then you would know that append, pop, these are fairly commonly used methods with lists. Most importantly, we are also going to see the time complexities taken by these methods. For example, insert, pop, remove, and so on and so forth. And we'll also see how to delete an item present on a particular index in a list. So there is all these things that we will be covering in this video. Let's start and look at them one by one. Okay, so let's begin by seeing how to create a list. So let me uncomment this line. So you can see that what I've written is that L equals to 2 empty squared brackets, open and close. And this is how we create a list in Python using using squared brackets. So this will create an empty list object for us, and L will be the variable that will be pointing to that empty list object. Let me print L and show you the output. So you can see that it prints the empty list object. Another thing is that you can also create list by using the built-in list class. And this will give you the same thing. And you can see that I still get the empty list object. Why you would want to create the lists like this? What I can certainly say is that, for example, if there is a code base which is not using type hints, then you may prefer creating a list like this, so that if someone who is not knowing about Python much and is looking at your code will understand that you're actually instantiating a list. However, if you're creating a list like this, then person needs to understand that empty this squared, open squared and closed squared brackets are actually going to create a list. But anyways, so this is how you create a list. Fairly simple. Let's comment this out and move ahead with the second concept. So how do we initialize a list? For initializing a list, you can simply fill in the values that you want your list to get initialized with. So for example, here I have filled it with integers and with comma separated integers, and every integer will be representing a particular index. The indexing start from 0, which means this particular index will be index 0, then this will be index 1, 800 will be located at index 1, then 2, 3, 4, and so on and so forth. So after this, if I try to print the variable L, then you can see that it should print the list with all the values, and that's what we are seeing here. So 400, 800, 200, 600, 1200, all the sequences with the sequences intact. And this is how you can initialize a list that you're creating. Let's move on to see how to perform indexing in a list, right? So as I have already told that the indexing starts from 0, which means 400 is located at the index 0, 800 is located at index 1, 200 is located at index 2, and so on and so forth up to index 4. Now, if I try to print, now, first of all, if you want to index, if you want to perform indexing, then what you have to do is that, let's say that I have created a list, something like this. So this is a list that I've created. Now I want to, if I have to do any sort of indexing, for example, let's say I want to find an item that is located at index 2. So 0th is 400, 1 is 800, and 2 is what the index that I'm looking for. And I want to see what is the item stored at index 2. It's 200. So what I'm going to do is that I'm going to put L and then put 2 here. So this will tell me what item is located at index 2. So if I want to see that, let me print this out as well. So if I run this, you can see that 200 is printed in the output. I'll run it again. So it gives me the output 200. So let's say that I want to find out the item that is located at index 0. And if I run this, you can see that at 0th index, it tells that the item that is located is 400. So that's what we can see here. At 0th index, 400 is located. Another thing that I would like to tell you is that let's say that you put an index, you give an index here, and let's say that that index is out of the range. For example, here we can see that the allowed values of the indices are 0, 1, 2, 3, 4. But let's say if you give 5, here and you try to print, then you can see that it throws you an error, and it says that it throws you an exception, and the exception is called index error, and it clearly mentions that the index that you have given is out of the range, right? So that's how you can know that the index that you're giving is out of the bound or out of the range. So another thing that at this point that I wanted to tell you is, okay, so what we have seen right now. So we have seen that the allowed index values are 0, 1, 2, 3, 4. And when we tried to index using the integer 5, then we got the list index out of the range error. But which means if I try to do 5, I got this error. If I try to index using 6, I should get the same error. Sorry. So if I run this, if I try to index using 6, I should get the same error. But what if I try to move towards negative? So we had from 0 to 4, but let's say if I try to move to -1, then what happens? So this is an interesting concept in Python, that if you try to move towards negative index, then what Python does is that -1, which is the first integer on the negative scale, while moving from right to left, then -1 is actually looped back. It is looped back at the last item. So, okay, let me tell you that. So let's say that I have this in below. On top, I have like positive index, and here I'll keep negative. So what am I going to do is that this is going to be -1. That's what I wanted to say. So this is going to be -2, and this is going to be -3, and this is going to be -4, and this is going to be -5. Sorry. -5. So I think they are slightly shifted. Let me move them a little closer to the item. And yes, this is what I wanted to convey. So if you're at 0th index, you are looking at item 400. If you are at first index, you are looking at item 800, so on and so forth. When you are at index 4, you are looking at item 1200. But when you try to index using 5, like the integer 5, then you go out of the bound. You get the index error. But when you move towards negative, when you're looking at index -1, you are actually pointing to the item, the last item in the list, which is 1200. But you try to go more negative, you'll see -2 is actually pointing to 600, -3 points to 200, which is in the reverse order, and so on and so forth up to -5, right? But when you go to -6, then hopefully you should again see an index out of the bound error. But let's see if that works. Firstly, let me try to index using -1. And what do we hope? What do we expect to see? We should be seeing 1200. So let's see. Yes. So that's what we expected, and that's what it printed as the output. If we try to print, let's say another index, which is -4, then if you do this, you'll see 800. But let's say that I want to print -6. As I said, -5 is 400, but -6 again goes out of the reach. And at this point, you should again see index error. And yes, so -6, when it tries to access an item located at the index -6, it throws an index error exception, and it says that list index is out of the range. So this is a pretty interesting concept in Python. In most of the cases, you will be using the positive indices like this way, because it's easier to read, easier to track. This is used in special cases, but it's good to know about them. So let's move ahead with the next section. But before we move ahead, let's see what is the time complexity of index operation. For example, if I am doing an indexing, let's say I want to find the item that is present at location 4, then what is the time complexity of it? So in this case, we have taken an example and we have just stored like 5 items or 5 integers in the list, but in actual, it can be a very large list. The size of that list could be could vary up to like n items, right? We don't know the value of that n, and it is presumably very large. So in that case, let's say if the number of items present in a list is n, then what will be the time complexity of indexing this way? Let's say I want to index the last item and I will have to do n minus 1, right? So for example, what I'm trying to say is that if a list that is having n items, then the integer range is from 0 to n minus 1, right? So here the size of this list was 5, from 0 to 5 minus 1, which is 4. This was the range of the indices. But in actual, because the number of items could vary and it could be very large, we denote it using n. So what will be the time complexity of, let's say I want to find the last item, which is, it could be n minus 1, right? In our case, it's 5 minus 1 because there are total 5 items, 5 integers. But in actual, it could be n. So what will be the time complexity? Does it have to go through all the items to figure out what is the item stored at the index n minus 1 or what it should be? Actually, it turns out that it's going to be order of 1. Actually, I should be writing a comment. So time complexity is going to be order of 1 for indexing. So this is going to be the time complexity. This is a constant time in which an index operation can be performed. Why is that? So basically, Python stores the address of the first location, and given an index, Python just needs to compute the address of the location based on the index that is provided. For example, if you give the index to be 0, then Python knows that 0th index means the first location. Let's say if you gave the index as 3, then what Python does is that it computes the address of the index 3, which is 0, 1, 2, 3. It computes the address of the item which is located at index 3. And this is a mathematical operation. It knows the first address, and it is just a mathematical operation, just a constant time operation that is used to compute the address of the item that is located at index 3. And that's why this is just a constant time operation. So let's move ahead and see how to find the length of a list, right? So this is pretty simple, I think simplest of all. So it just needs you to have this thing. So you can use the built-in len function of Python, and you can just pass in your list object. So let's say that I'm just copying this here so that it remains in this context, and I'll just comment this out. So if I want to get the length of this particular list, I just have to do this, and this is going to give me the length of that list. So what is the length of this list? Length is 1, 2, 3, 4, 5. It's going to give me 5 because there are 5 items. Length is equal to the number of items that are stored in a particular list. So let me clear the terminal here. And now if I run this, you can see that it has printed 5, and 5 is the number of items that are stored here. So let's say if I just want to increase the number of items in my list, let's say I increased it like this. Now I've added 2 more items. So it should be 7 now. And yes, it prints 7. So I hope that you understood that computing length is just using the len function in Python provided by Python. You can just pass in your list object. So now that you know how to compute the length of a given list using the len function, then what is the time complexity taken by this len function? So do you think that time complexity? So do you think that it is going to be order of n, which is like iterating over all the items in that list and figuring out how many items are present in that list? Or will it be something else? So anyways, let me tell you that this time complexity that is taken to compute the length of a list is actually order 1. And this is because Python actually keeps track of this length, the length of this list in a variable under the hood. So length of this list is already stored in some variable under the hood by Python. And when you run this len function and you pass your list object to it, then what this len function does is that it under the hood just reads the value of that variable that is invisible to us, that is created by Python under the hood or created by Python's library under the hood. And it just length function, what it does is that it just reads the value of that variable and it just shows that to us. So it's just again reading a variable, that's all. No matter what is the size of this list, it just has to read the value of a particular variable. And that's why this time complexity is order 1. It's a constant time operation. And again, now what we have seen so far, that if you try to perform an index operation on a list, it's going to take order 1 time complexity. And if you try to find the length of a particular list using len function, then it is going to give you the length of that particular list in order 1 time. So let's move to the append method in lists, which is probably after you have created a list, which is, I feel that this is the fairly common or the most commonly used method in list. You will mostly be finding yourself in a situation where you are always adding items to your list. And that's where the append method comes into the play. So what this method is about, it basically adds an item to the end of the list. So I have already written, I forgot that I've already written it here as well. So it pushes the item at the end or adds an item to the end of the list. Let's see how it does it. So I'll just copy this particular list from here and I'll comment these two lines and I'll paste it here. So this is the list. Now let's say that I want to append another item to this list by doing l.append. And then what I have to do is that, let's say I want to add 2000 or let's say 2500. I want to add 2500. Oops. So what I can do is that, let's say after that I can print it. And now let's see what is, now let's see what is the final list. Now you can see that we had up to 1600. Now you can see that after 1600, 2500 is added to the end of that list. Right? So that's all what append does. It actually adds an item to the end of the list. And I think it's fairly simple to understand. Now let's see what will be the time complexity of storing the item to the end of the list or adding an item to the end of the list. Time complexity of this append operation. So what we are trying to do is that we are trying to find the time complexity of this append operation. Now, what do you think? What will be the time complexity? Just try to think. Now, let me tell you, you can pause here and think of it, but let me move ahead. There are cases where Python has, let's say in this case, Python has stored 7 items, which is 7 integers, but there is no space for adding the new item. We are trying to add a new item to this list, but let's say there is no space. In that case, what Python needs to do is that Python needs to allocate the space for a new list, or basically Python needs to allocate a bigger space for a new list, and then it will copy individual items to that list, which means that it needs to iterate over this list and individually add or copy the items to the new list, which is also bigger in size. And that new list will also be capable of storing 2500. So in that list, in the end, Python will add 2500 at the end. So in that case, what happened? What actually happened? Python allocated a new space, a bigger space, copied individual items from the older list to the new list, and then added 2500 at the end of that list. So this seems like an order n operation, right? It had to iterate over all the items in this list. However, it turns out that Python sometimes, Python in most of the cases, over allocates the space, which means, let's say that we have 7 items here. Python might have allocated the space to store up to 14 items. Now, because we have stored only 7 items, which means we still have empty spaces for 7 more items. So in that case, what append will do? If you try to append, Python just needs to store that 2500 or the new item in the next space, because there are 7 spots that are empty, 7 more locations that are empty in that list. So in that case, it will be a constant time operation. It doesn't need to iterate over all of these items. It just needs to store that new item to the next location, right? So you need to understand what will be the time complexity. So it needs a deeper analysis. especially it needs amortized analysis. And I have a section of the next section in this video is actually going to talk about that, how append works or how list works and some internals of the list. So if you're interested, you can jump to that section also. After watching this section, you can look at that section and that will help you a lot. But let me tell you that the amortized analysis says that the time complexity of the append operation is constant time, which is order 1, which means if you try to append an item to a list, doesn't matter Python has over allocated the space or not, the time complexity turns out to be order 1 amortized based on amortized analysis, right? Or you can say that average also. Most of the times amortized and average are used interchangeably, but there is a conceptual difference between these two. But you can think of it as order 1 time complexity for an append operation in a list. So now let's move on to the pop operation. So before I move on to pop operation, let me just copy this list here, and yeah. So we are now looking at the pop operation. So we have our list which contains random integers, and we want to see how pop operation works. So pop operation by default removes the last item from the list. So let us quickly check that. So I just invoke the pop operation on the list. And now if I print our list, then we should see that the last item should be gone. Yeah. So we can see that 1600 was the last item that was present in our list. And in the output, you can see that 1600 is not there, which means pop operation actually popped it, or it actually removed it from the list. Pop operation also removes the item from a particular index. So for example, if you want to remove an item located at a particular index, then you can remove it by passing an index to the pop operation. So what do I mean by that? So let's say that I want to remove 1200. So 1200 is located at which index? So it's 0, 1, 2, 3, and 4. I suppose it's 4. So I can just pass 4 here. And now if I run, so you can see that 1600 will be there, but what we expect is 1200 should be gone from the list. So if I run it, so you can see that 1600 is there, but I cannot see 1200. So pop operation has removed 1200 from the list. So if given an argument, if pop operation is given an index as input, then it removes the item from that particular index. If nothing is provided as an argument, then pop operation will by default remove the last item from the list. So I hope that I have made it clear how pop operation works. Before we move on, I would like to just show you the definition signature of the pop operation. So you can see that the signature of pop operation looks something like this, and it takes in this index. So it takes in this index argument, and it is set by default to -1. So if you know, earlier in this section of the video, I have told that -1 actually points to the last item in the list, right? So by default, it is set to -1. And because it is set to -1, if we don't give any argument, if we don't pass any argument to the pop operation, then it is going to remove the last item from the list because of this default -1, which is set here. So you can also see that pop operation is going to return us the generic type, which is basically whatever the type you store in your list, it returns that type. I'll tell you what it is. So basically the item that you're going to remove, pop actually returns you. So let's see that. So let's say here I have provided 4, which means we were removing 1200. So pop will actually return you that item. So I'll just do removed item. And here I'm supposed to get the 1200 as in the removed item. So basically pop operation should return 1200. So let me print this removed item. And if I run it, so I get 1200. So pop operation, now what do we know extra about pop operation? So pop operation actually removes an item from an index, from the provided index, and actually it returns that particular removed item as well. So if I don't give here anything, then it is going to remove the last item from the list, and it is also going to return that particular removed last item. So you can see that now it has returned 1600. So I hope that it made sense to you that pop operation by default removes the last item. It returns the removed item as well. Also, if provided any index, it is going to remove that. It is going to remove an item present on that particular index. And also, of course, it is going to always return the removed item. So let's talk about the time complexity of this operation. So what do you think will be the time complexity of the pop operation? So let me tell you this. Pop operation, the time complexity of the pop operation is order 1 when we are always removing the last item. Because it doesn't matter what is the size of this list. By default, the index points to -1. And we have already seen that indexing a list at the end is very easy. It's just one mathematical operation in order 1 time. So locating the last item in a list is just constant time operation. And it just needs to remove that, right? So it will remove that in constant time and rest of the list will remain as it is. That's all. However, which means, okay, let me write that. So order 1. So when removing the last item from the list, right? Now, but what if we want to remove any arbitrary item given at a particular index, right? So if we give an arbitrary index to pop operation and it removes that item, then what will be the time complexity? So in that case, assume that if you are giving the index as 0, then it is supposed to remove the first item, right? Locating the first item will be just constant time operation. But what will happen after that? Because the first item will be removed, then there will be a void there will be a blank spot, empty spot at the first location. So in that case, what needs to be done is all the items needs to be shifted back one location, which means after first item is removed, then 800 needs to be shifted one position left. Similarly for 200, 600, 12, 14, 16, and up to the last item, right? So in the worst case, I think you can imagine that removing that particular item will be a constant time, but after that it needs to rearrange the items in a list so that they form that continuity, right? So there should not be any, for example, you remove this item 200, then you cannot have a list which should have an empty space or empty location in the end, right? It will point to none. So it needs to shift all the locations, all the items located after that one position towards left. Because we were talking about removing the first item, then all the n-1 items should be shifted one position towards the left. So in the worst case, the time complexity is supposed to be order of n-1. So when this will happen? When removing the first item, or in the worst case, basically in the worst case. So this is how the time complexity of pop operation would look like. So now we should move on to the insert method. So now let's start with the insert method. So before we start, let me comment this out, copy the same list and paste it here. So we have the insert method now. So we have the same list consisting of random integers. Now, insert method actually inserts an item on an index. For example, let's say that I want to insert an item at index 1, which is 2500, for example. So what insert method will do, it will take an index and an item that you want to insert on that particular index, and then it will shift all the items after that index one position to the right. Okay, let me demonstrate that to you. For example, l.insert, let's say that I want to insert an item on an index 1, and let's say that it is 2500. Now, if I print the value of L, then let's see what it prints. So you can see that index 1 is now 2500, but earlier it was 800. So what happened to the items after 800 till 1600? They all are moved one location towards right. Earlier, 800 was located at index 1, 200 was located at index 2, then 3, 4, 5, 6. 1600 was located at index 6. Right now, 0, 1, 2, 3, 4, 5, 6, 7. Now 1600 is located at index 7, which means all the items that had to come after 2500 were moved one location towards right. And that's what we see. So I think in the inserting is pretty simple. It's simple to understand. And I hope that you would also be able to understand its time complexity. So time complexity is also fairly simple to understand because inserting will in the worst case take order of n time complexity. For example, if you want to insert at location 0, which is index 0, then all the n items, right, needs to be shifted one location towards right in order to accommodate the item that you're going to insert. So here, in order to accommodate 2500, we had to shift all the items that had to appear after 2500 towards right by one location. So I hope that you would understand that time complexity for this is going to be order of 1. So I hope that was fairly easy to understand about insert. So now let's move on to the remove method of lists. Now let's understand about the remove operation on a list. So basically remove works in a fairly simple way and very intuitive, that it removes an item that you're giving as an argument to it in a list. For example, I'll do l.remove and I want to remove, for example, 1400, right? 1400 is here. Now, if I have to remove 1400, I just have to pass it as an argument. Now, if I print the list, then you can see that 1400 is missing from the list now. 1400 has been successfully removed by this remove method. Now, how is it different from the pop operation that we have seen earlier? Pop actually took the index of the item that we wanted to remove, but on the other hand, remove actually takes the item itself, not the index of that particular item. So I hope that difference is clear here. And also pop by default removes the last item. However, you need to provide something to remove. It's this particular value, right? This is the value, this is the signature of remove, and it doesn't return anything unlike pop. Pop actually returns you the popped element, but remove actually doesn't return you anything. It just deletes that item from the list. That's all. So it takes an item that we want to remove, and you can see that this particular item is also not optional. So it's not like pop. If you don't provide anything to remove, it's going to throw you an error. So let me run this, and it tells me that list.remove, it takes exactly one argument, but none was given, right? So you need to pass compulsorily the item that you want to remove. So let's say I pass 800 this time, and if I run, you can see that 800 was removed from the list. Another thing that I want to tell you is that let's say that I have multiple occurrences of 800. So I have 800 here as well. So in that case, remove is actually going to remove the first occurrence of 800. So you should see the 800 that appears after 200 or appears before 600. That should still be present after this remove is executed. So let me run again. So you can see that 400, the 800 that was between 400 and 200 was removed. So 400 and 200, now 200 comes right after 400, and the 800 that was in between 400 and 200 was removed. And the second 800 that was between 200 and 600 is still there. So it just removes the first occurrence of the item that you want to remove. So I hope that it was clear to understand how remove works. Another thing to note here is that let's say that you want to give, you're actually passing an item that is not present in the list. So for example, I pass in, let's say 3000, right? So 3000 is not present in the list. So in that case, remove is going to raise an exception. So let me run this. And yes, you can see that it raises an exception which tells value error, which means that particular item that you have passed in order to remove is actually not present in the list, right? So it's going to raise an exception. So Anyways, I hope that it was easy to understand what remove does. And I hope that it is also fairly simple to guess what will be the time complexity for remove operation as well. So it should be almost same as like the pop. For example, if you remove any arbitrary item from in between, for example, if I remove 800, this 800 from the list, then I need to shift all the items after that backward or towards the left by one location. So it in the worst case, it is going to take order of n time, order of n minus 1, or which is actually equivalent to order of n time. So I hope that you understood what is the remove operation. So let's move on to the final operation that we want to look at in the list is the del operation. So now let's see what is the del operation on a list. So basically, let's say that I do del L, right? I'm trying to, what this will do is that this will actually remove the entire list object from the memory, which means this entire list object will be wiped off from the memory and you will no longer be able to access it. So let's try to access, or let's try to print it and see what is the output. So before I run it, you can see that linter has already started giving me the error and it says that L is unbound. So essentially Python's interpreter should also give me something like that, that L is unbound or undefined. So yeah, you can see that it gives the exact same error, which is name error, and it says that L is not defined. So this is how you can delete the entire list object, right? Now let's say that you want to delete a particular item in a list located at a particular index. So you can do that. So let's say I want to remove the item that is located at 0, 1, 2, 3, 4, let's say 4. I want to remove 600. So it is located at index 4. So I can do this. Now, after this, if I try to print the list, so I should not see 600 in the output. So before I run this, let me clear it. And now if I run it, you can see that 600 is not present in the list. So this is another way of removing an arbitrary item from the list based on its index. So earlier we have seen pop, which also removed an arbitrary item from the list based on index. Del is another way of removing an arbitrary item from the list based on its index, right? So you can pass in here the index of the item that you want to remove. So another thing about del keyword is that you can actually give here the slice operator. For example, if I give 4 to 7, right? So this is going to remove the item present at index 4, 5, and 6. It will not remove items present at index 7, but it will remove all the items located between 4 to 7 minus 1. 4 till 7 minus 1. So what are those items? So it's 400, which is 0, 1, 2, 3, 4, which means it will start removing or deleting items from 600, position 4, then 5 is 1200, 6 is 1400, then 1600 is 7, but it won't remove 1600. So it will remove these 3 items, right? So you can think of it as simple, like regular slice operator works. So it is like start and then stop. But it will function, or it will remove all the items. But what are the items that it is going to remove? It is going to remove items from start to stop minus 1. So from start to stop minus 1, from start, which is 4, to stop minus 1, which is 6. So from 600 till 1400, these 3 items it should remove. So I'm printing it again. Let me run it and see. Yep. So you can see that it has removed 600, 1200, and 1400. So you cannot see 600, 1200, and 1400. And item which was located at the index 7, which was 1600, it's still there. So you can use this as well. So you can pass in the slice operator as well. So let's move on to the time complexity of this operation, which is again order of n, because removing any arbitrary item from the list is actually going to be followed by moving all the items that are present at the right location towards left. So because using del, you can also remove the first item like this. So in this case, what will happen in the worst case? All the items that were after the index 0, they are going to be moved by one location towards the left. So these left shifting all the n-1 items is actually order n time complexity. So in the worst case, it's order n time complexity. So with that, I hope that you have understood all the commonly used operations on list. And if you have any doubts, then put that in the comments. I'm going to help you out. In this part of the video, we are going to see two more concepts, and we'll just go one step ahead and try to understand list in a better way. So first part that I would like to explain you, which is how lists, particularly in Python, can store multiple types of data at the same time. So for example, a list in Python can store an integer and like it can store an integer, a string, or any type of data at the same time. If you're coming from C background, you would know that a list or an array created in C can store only one type of data, right? However, in Python, we can store multiple types of data at the same time, and we are going to see how is that implemented, what is the mechanics behind that. And next thing that we are going to see here is that how append method works in order one time complexity overall. So we know that if there is a list and it has some spaces filled and some spaces empty. So for example, this is filled with x1, x2, x3, and then x4. Let's say 4 items. There are some spaces empty to occupy 4 more items. Now let's say that you're trying to insert x5. Then this insertion is going to take just order one time complexity because there are some empty spaces out there. But let's say that you have filled x5, x6, x7, and x8. Right? You have filled total all the 8 items in the list, and now list is full. But let's say you also want to fill an item called x9, but there is no space left. In that case, I have briefly introduced you previously in this video that Python is going to create another list, which will be as big as double the size of the previous list. So let's say the total item that previous list could store was x, however 8 in this case. Then the new list will be able to occupy, or it will be able to store up to 16 items. So 2x. So it will create a list as big as 2x from the previous list, like 2x of the previous list. Now, after that list is created, it is going to copy all the items in the previous list to the new list. So it will copy all the items, and then finally it is going to store x9 right after that. So what does this mean? So this operation actually, in this case, order n or append operation is going to take order n time complexity, right? So sometimes it takes order 1 and sometimes it takes order n, but we concluded that overall it takes order 1 time complexity. If it is averaged over a large number of data set, then it actually comes around order 1, and we are going to compute that. I hope that you'll get more idea with understanding these two concepts, and you'll be able to understand about list in a better way. Let's see how lists in Python store multiple types of data at the same time. So assume this is a list that I've created right now, and it is known by variable a. Then every list is going to have its own memory address, right? So let's say 0x000 and then 0x04. So I'll just erase it again and I'll write it again. So 0x00, then 0x04, 0x08, 0x12, 0x16, and so on and so forth. And every cell is also going to have an index. So index is going to start from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So assume this is a list, right? Now, if it was a C, if you were writing code in C language, then you need to define that what kind of data that you're going to store in this list. So let's say, for simplicity, again, let's say if it is integer, right? So you can only store integers in all of these cells. So let's say that you have stored 100, then 120, then let's say 85, then 90, 82, 71, 5, 2, something like this, some random integers. Now, we know that in Python, we can store multiple types of data, but I just wanted to explain you the setup that how it used to work. It works in C. So in C, every cell can store only one type of data. However, in Python, on the other hand, the entire setup is same, except that in Python, I'm just trying to make the same list 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's say the address is also same 0x00, then 0x04, then 08, 12, 1620, and so on. Now, in case of Python, instead of storing the actual value or actual object, it actually stores the address. So you can think of this is a cell. Think of it like this. This is a cell. It has this memory address, but this cell will store another memory address. So let's say that it is storing 0x100. And this is the memory address of the actual object. Let's say integer object, where your value, which contains your value. Let's say you want to store 100, your 100 value will be stored in that object, which is present at the memory address 100. Let's say this is index 3 and this stores another address, some completely random memory address. So it will be 0x, let's say 40, something like this. And this will be the memory address of the object that is having a value. Let's say it's a string. Let's say this is a string, right? So let's say this is another memory. This will also contain another memory address. So let's say 0x80, and this contains an object which is basically a dictionary. So it has some key and a value. So what am I trying to convey here? So in case of Python, we, instead of storing the actual values like this, we actually store the memory addresses in the list. This helps Python to store different types of data at the same time. So what we need to do in case of indexing, we just need to index. Let's say I want to find what is the item located at index 4. So we know that address starts with 0, and then it will be just a simple mathematical calculation. So every cell is of 4 bytes. So 4 into, let's say 4, right? So this is going to give me a memory address of 16, and it will just point to this memory location, and this will contain the address of the item that I want to access. So let's say it contained the address, let's say 54, something like this, some random memory address. And I wanted to see what is the item that is located. And let's say the item that was present here is a string, right? So a string is like, let's say hello, something like this. So I can access the item like this in Python. However, in C, in languages like C, if you locate the cell given an index, if you locate the cell, so let's say I want to access what is stored at location 6, index 6, then I can simply compute its memory address, and that memory address, which is this cell's memory address, will contain the value that I'm looking for. It doesn't store any other memory address, unless and until you actually created an array of double pointers, but I'm not talking about that. In Python, it generally happens that it actually stores the memory address or a pointer to the actual objects rather than storing the actual objects itself. So I hope that you're getting the idea of what I'm trying to convey. So this helps Python store multiple types of data at the same time. This is just to give you an idea how Python manages and stores multiple types of data at the same time. Now let's try to understand how append method in a list works in order one time complexity. So I hope that you have seen the previous section of the video where I have explained what append does in code, but let's try to understand a little theory behind it, like how it works in order one time complexity. So okay, just before I actually get on to that, let's try to understand what actually append does behind the scenes. So let's say that we have a list which just contains one item. Let's say it contains an integer. Let's say integer is some things, let's say x0, right? But there is no space to add another item in the list. So it just contained one item here. Let's say I wanted to push another item. So in that case, what Python will do, or append operation will do behind the scenes, is it will create a new list of double the size of the previous list. So this can hold up to 2 items, right? And it will create and copy the previous item to the new list, all the items of the previous list to the new list. And then I was trying to insert, let's say x1, so I can put x1 here. Now let's say at this point I want to insert x2, but I cannot do that again because again there is no space for doing that. So in that case, Python will again create a new list of double the size of the previous list. So previous list was of size 2, or it can hold up to maximum of two items. Now the new list can hold up to the maximum of 4 items, and it will copy both the items from the older list to the new list. So x0, x1, and then it will place x2. Now let's say I want to put or insert x3, append x3 at the end. Now that can be done. At this point, there is no need to create a new list. So that can be done easily in the same list, right? So x0, x1, x2, x3, right? Now, till now, let's try to understand what happened. At this point, it actually created a new list. At this point also, when we tried to insert x2, so when we tried to insert x1, it created a new list because there was no space. When we tried to insert x2, it created a new list because there was no space. In x3, there was no need to create a new list. So this can be termed as order 1 operation, right? Assume that when you're trying to insert x2 and there is no space and you have around n items in the list. So then Python will have to create a list of size 2n and copy all the n items from the older list to the new list, right? But we are at least here, we are certainly sure that inserting x3 was just order 1 time complexity operation. Let's do some more, right? Now let's say I want to store x4. Now I cannot do that again because there is no space. So in that case, a new list will be created that can hold up to 8 items, right? So 1, 2, 3, 4, 5, 6, 7, 8. Now here, all the items from the previous list will be copied to the new list. So x0, x1, x2, x3, x4 that I was trying to insert will be placed here, right? Now this list is capable of holding 3 more items, which means at this point, if I try to insert x5, it can be done in order 1 time. So x5. If I try to insert x6, it can be done here in order 1 time. If I try to insert x7, it can be done here in order 1 time. So you can see that there are a mix of order 1 operations and some order k operations where k is the size of that older list. For example, here the k was 1 because we created a list of size 2. So 2 into 1. At this point, the size, at this point, the size of this list was 4. So we created a list of size 2 into 4, right? So let's say this 4 was k, so order of 2k, something like that, an operation, but again, order of k. So some operations are order 1, some operations are order k, right? So I hope that you understood what are those order k operations that I was talking about. If you didn't understand, then let me tell you again. So there are operations that are going to take just order 1. For example, let's say here, we were trying to insert order x5, right? We were having 3 empty spots. So x5, insertion of x5 in this empty spot would take just order 1. And insertion of x6 in this space at this empty spot will take just order 1. Insertion of this x7 at this empty spot will take just order 1. But if we try to insert x8, right? At this point, Python append operation will have to create a bigger list, which will be double the size of this list, and copy all the items from this list to the new list, right? I'm just terming those append operations that will run for order k time complexity. I'm just terming it order k for now. But at least you should get the intuition that whenever an append operation happens, then if every time we are doubling the list, right? So list will be of size 1 first, then it will be doubled to size 2, then it will be doubled to size 4, then it will be again doubled to size 8 and so on, right? But all the operations in between will take order 1 time. Whenever we have to double, that's where the costly operation comes in, right? So let me just summarize this. So the append operations that we are actually trying to do can be categorized as the constant, which is order 1, and then costly, which is order k. That's what I was saying, where Python needs to create a new list. So these are the two categories of the operation. We know that there are costly operations and we know that there are constant operations. So let's see how many such costly operations we are going to see. So let's say we inserted the first item, but when we insert the second item, we need to double, right? So it will be operation of 2 units. Then to insert the third item, we need to double it again to 2 plus 4. Then from 2 to 4, it is going to create. If you didn't understand, then let me tell you. So we had this first item. In order to insert the second item, it has to double the list. Then you inserted 2 items. Now, in order to insert the third item, it has to double the list. Then it will create this 4. So I've just written 4 here. Now we have 3 items already. We inserted 3 items. Now when we try to insert the third item, then it is going to just take order 1 time complexity, right? Just order 1 time complexity. So it will be inserted here. Now in order to insert, when we will try to insert the fifth item, which is how many items we have inserted. So this 1, 2, 4 and 1, this is just for inserting item 1, we took order 1. For inserting item 2, we took order 2, like O of 2, or basically 2 units of operations. In order to insert the item 3, we took 4 units of operations. And then inserting for our item 4, we took again just order 1, just 1 unit of operation, because we just had to copy our item that we are trying to insert because there was a free or empty spot available. Now, in order to insert the fifth item, we again need to double it. So it will be 8, right? So why? So it needs to create another list that will be of size 8. So in order to insert I5, we took 8 units of operation. Now, how many items we have inserted? 1, 2, 3, 4, and 5. So it should be 8. So 3 more items. Now let's say I want to insert the sixth item and it is going to take just order 1. Then I want to insert 7th item, then it is going to take just order 1. This is the 7th item. Then I want to insert the 8th item, which is I8, then it is going to take just order 1. Here is the 8th item. But when I try to insert the 9th item, then it is going to take order 16. I hope that you're getting the pattern. So there are operations which run in the progression of 2 plus 4 plus 8 plus 16. So if I just divide them, so there will you can categorize it like this. So there are order 1 operations, some number of operations. So let's say that number is x. Then there are operations that run like this: 2 plus 4 plus 8 plus 16 and so on. Right? So let's say there are k such operations, or let's say there are y such operations that are accounted for 2 plus 4 plus 8 plus 16, right? And then there are x operations that are order 1. Now let's say that x plus y is total n, which means we have inserted total of n items in our list. I hope you're getting that. So let me clear this space and then probably it will make more sense. Okay, so what I was saying is that there are, let's assume that there are x order 1 operations. Then there are operations where Python has to double the list every time. So 2 plus 4 plus 8 plus 16 plus like this. And let's say these are up to y operations. So how many insertions in total are we performing? How many insertions? We are performing x insertions that happen in constant time, and we are performing y operations that in which first operation took 2 units, second operation took took 4 units, third operation took 8 units, and so on and so forth. But there are total y insertions or y operations. So x plus y, let's say it is n, which means we have done total n insertions. I hope I'm making clear here my point. I'm just clean out more space. So I hope you understood that we are making a total of n insertions. And this is the, if we sum this thing, right? That's where we will find our time complexity. Okay, so what we have assumed is that x plus y is going to be n. And there are y insertions that work in a geometric progression, right? This is a geometric progression. And there are x operations, x append operations that take just order 1 time complexities. And x plus y equals n. Now, let's try to focus on this particular geometric progression. So 2 plus 4 plus 8 plus 16 plus up to 2 power k. Assume this, right? Or because we are saying that there are y insertions, so let's make it a more generic geometric progression. So 2 power 0 to up to 2 power y. Move ahead and actually generalize it more. So 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3 plus 2 power 4 and so on and so forth plus up to 2 power y. And 2 power y is actually, I mean, this means that 0, 1, 2, 3, 4 up to y, which means there are total y plus 1. There are total y plus 1 such insertions where append operation needed doubling the list, or basically it was a costly operation. Now, at least try to assume or try to think that when last time, when it was doubled last time, basically when the last operation where the array was doubled, then it was doubled and made 2 power y. So you could think of that this would have led to the size of the array, which would be equal to n, right? Try to think about it. So this would have led to the size of the list equivalent to n. Because that's in these operations only, we are dynamically changing the size of the array. And when the last operation would have happened, when the last operation where append actually doubled the size of the array, then the size of the array would have become n. And that's why we are saying that we have total of n insertions or total of n items in the array. So I'm saying that 2 power y would be equal to n. So this is what would be the case. 2 power y would be equal to n. Now this is geometric progression, and this would lead to the sum of 2 power y plus 1 minus 1. This will be the sum. Now we know that 2 power y would be written as 2 power y into 2 minus 1. And this will be equal to, if I replace 2 power y with n, then n into 2 minus 1, which is 2n minus 1, like this. So this geometric progression resulted in this. And let's say this, we said that there are total x number of operations that took order 1 time complexity. So x into order 1, right? So let's try to sum them up. So x into order 1 plus 2n minus 1. Right? This is the total sum. This total sum is equivalent to this. Now x into order 1. We know that value of x is actually less than n, because we said that x plus y equals to n. So x will be equals to n minus y. And these are total number of y operations. So in worst case, again, because we are anyway doing average case analysis or amortized analysis, but let's say that maximum value of x could be what? It could be n. So let's try to use n. So n plus n into order 1, right? Plus 2n minus 1. So again, this will be n plus 2n minus 1. Overall, it will be 3n minus 1. So this is the time complexity of inserting all the n items for n insertions. Let me clear out some space again here. So we were left with n into order 1 plus 2n minus 1. So this will be n plus again 2n minus 1, right? So this will be 3n minus 1. So this is the total time complexity of n insertions, which means in order to insert n items, or actually we can roughly say that there are 3n. This is equivalent to 3n. Now, what will be the time complexity? This is for n insertions. Now, what will be the time complexity of just one insertions? For n insertion, it took 3n. Then for one insertion, it will be 3n by n, which is 3 units, which is again order of 1 time complexity. So for one insertion, which means for one append operation, we have proved that it will take order 1 time complexity, despite that Python or append operation was occasionally doing such doubling of the list and creating double size of array, and all those operations were included. But over the period of time with more number of operations, when over the period of time averaged over more number of operations, it turned out that append on an average takes just order 1 time complexity, right? I hope that it made sense to you that overall append operation is going to take order 1 time complexity. So if you have any doubts regarding this, then please put that in the comment. I'll definitely help you out. I'll try to address your problem, and I'll try to link more resources where you can find the details of how to prove that append operation takes just order 1 time complexity. Reading them also will help you to understand about it better. But if you have doubts, then put that in the comments. I'm going to help you out.